Welcome back. In this lecture, we will look at an important aspect of battery, which is how does the cell potential of a battery change as it discharges. So we will look at it in two manner. In this lecture, we will mainly look at thermodynamic consideration. In the next lecture, we will look at kinetic factors. So what affects the cell potential? If you ask that question, the main feature is the chemistry of the battery. So here we plot cell potential in the y-axis and the fraction of capacity discharge. So when the battery has full capacity, if you look at the potential, um, different battery chemistries have very different potentials. So the two main advantages of a lithium-ion battery is that one is that it has very high potential compared to all other kinds of battery, and it's fairly light. Hence, it can be used for transportation applications also. So if you look at the voltage of a lithium-ion battery, it's almost twice that of the other most common secondary battery, which is the lead-acid battery. And it is much more than the alkaline batteries. Okay, so these are a class of batteries which are sort of related, which have related chemistry. Compared to this, the voltage of lithium-ion battery is twice or thrice as much. So there is no common accepted nomenclature. There's no consistency in nomenclature. Here we say lead acid battery. It gives no indication of what is the nature of the electrode. Here, this is LFP kind of cathodes. Okay, so NCA also gives you an idea of what are the components of the cathode. Okay, so however, there is no simple accepted consistent nomenclature across all battery chemistries. Okay, so just saying alkaline doesn't tell me what is the nature of the anode and cathode, but that's the way it is. So, but the take-home message is that lithium-ion battery has much greater voltage compared to other battery chemistries. So the reason for that is the exothermicity of the relevant redox reaction. That is as measured by delta G controls the voltage. And the voltage we are referring to is, let's say, the open circuit voltage at full capacity. So that is here. Okay, so you can have open circuit voltage at any capacities. Okay, so even when you have a battery that is 50% discharged, let's say, you can still measure the open circuit potential, but this voltage refers to open circuit voltage at full capacity. So this feature controls the open circuit voltage. So potential during the operation of the battery also depends on the kinetic factors besides just thermodynamics. Okay, so when you talk about thermodynamics, mostly we are talking about things at equilibrium. Okay, so when you say thermodynamic voltage, so we say that things are at equilibrium. That's when we can discuss the features of thermodynamics most rigorously. But when things are not at equilibrium, okay, there are some kinetic factors, rate factors involved. It's the conceptual underpinnings are more challenging. So we have to bring in other factors. We will go into these things. We have discussed some aspects, but we'll also get into these factors as we progress in this course. So what I'm trying to say is the potential during operation, when I say it depends upon kinetic factors, what I mean by that is the potential is also dependent on the amount of current that I'm extracting from the battery. Supposing I'm extracting very small current from the battery, the potential will be different at the state at the same state of charge. And if the current I'm drawing from the battery is much more at the same state of charge, the potential will be different. Okay, so this is what is meant by potential is dependent upon current or rate factors or the kinetic factors. Okay, so these aspects, to understand them, we have to look back at certain fundamental principles of electrochemical systems. We have covered this in previous lectures. These are called activation over potential, concentration over potential. Um, so these aspects affect the energetics of a battery. Okay, so both these factors depend upon the amount of current that is being drawn from a battery. So to understand this, you have to look back at the previous lectures. These are available in this YouTube channel under the playlist Introduction to Electrochemical Engineering. So especially three particular lectures. So this is on concentration, transport, polarization, over potential. Okay, so that is one important lecture. Then the conductivity of the electrolyte um, determines the resistance in the electrolyte, which in turn determines the IR drop in the electrolyte. This can be controlled by variety of supporting electrolytes. This is a very important feature of a battery, practical battery and any electrochemical system. So you have to understand this, um, um, think through this very carefully. And when you say migratory transport, we are referring to a particular transport mechanism. Okay, so there is three transport mechanisms that are of relevance: convection, diffusion, and migration. In many systems, for example, in battery, you don't have external forced convection. In most common batteries, you may still have such a forced convection in, let's say, redox flow batteries. But in most common batteries, all you need to worry about is diffusion and migratory transport. These are all technical terms. Okay, so you have to go back and look at these lectures to understand and refresh your knowledge of these factors. So another important feature is the activation over potential that is encapsulated in the phenomenological Butler-Warmer equation. So when we talk about rate processes in an electrochemical system, we can have two different rate processes. One set of rate processes are correlated with rate in the electrolyte, and other set of rate process involves the chemical reaction, rate of chemical reaction at the electrode electrolyte interface. Okay, so this, in a way, you have some intuition from your high school. Okay, so we have the Arrhenius equation, which tells which tries to correlate the rate of chemical reaction to activation energy present. Okay, so in a way, Butler-Warmer equation is an extension of Arrhenius kind of logic to electrochemical reaction. So all these three lectures are very critical. So your understanding of these lectures is very important to clarify this particular uh, notion. Okay, so this is a good time to pause and go through these lectures before proceeding ahead. So the state of charge controls the cell potential. So these are essentially thermodynamic consideration. And for every battery chemistry, there is a different way of understanding how the state of charge is related to the potential measured at a particular capacity. For example, in a lead acid battery, as we have already elaborated, what happens is that as the battery gets discharged, this is the reaction. There is lead, which is a solid electrolyte, lead oxide, another solid electrolyte, combines with H2SO4, you form lead sulfate at the electrode surface. Okay, so lead sulfate is also a solid that is deposited here, and you form water. So this is the overall reaction in a lead acid battery. This is not indicative of half cell reaction. So this has certain advantages when you think through the thermodynamics, because these three components, that is lead and lead dioxide, these are active material. These are the reactants in this reaction. And the products, lead sulfate, all three are solids. Okay. So when you represent the potential of a battery in terms of activity of the relevant components, the convention is that the activity of a solid is taken as unity. So those terms drop out of the cell potential. So you can just represent the cell potential in terms of activity of H2SO4 and activity of water. So in the in a battery under which has a lot of capacity, the concentration of H2SO4 is lot, and that gradually decreases. So activity is concentration times activity coefficient. So all these aspects have been covered in previous set of lectures under electrochemical thermodynamics. So if you're unsure of these terms and how these activity is correlated to potential, you have to look back at lectures on electrochemical thermodynamics, which we have covered under the playlist Introduction to Electrochemical Engineering. So in a sense, what is happening in a lead acid battery is that the concentration of H2SO4 is decreasing, and with corresponding changes in concentration of water. So these two thermodynamic factors can be correlated to potential. And this is also useful for empirical measurement of state of charge. If I just measure the density of the electrolyte, which gives me a measure of concentration of H2SO4, I can correlate it to the potential of a lead acid battery. So when I go to, let's say, another class of battery, which is a lithium ion battery with a particular LMO cathode. Okay, so here this cathode, which has a spinel structure. So what is indicated here, there are many things that are indicated. We'll go through this slowly. Okay, so this indicates the structure of graphite. Okay, and with lithium ions inserted in the graphite anode. When the battery is getting discharged, lithium ions get intercalated into the cathode material. Here we are using LMO as the cathode material. So this is a two-dimensional layered structure. Graphite has a two-dimensional layered structure. But here, LMO is not two-dimensional. It's not a layered structure, but it has channels. Okay, so which allow for insertion of lithium ions. Okay, so when lithium ions get inserted, they interact with manganese and manganese oxide in general. Okay, so the thermodynamics of the lithium ion battery with LMO cathode and graphite anode is dependent upon the interaction, two kinds of interaction, right? Two kinds of lithium ion interaction. The one interaction is when lithium is in the anode, right? So during discharge, lithium that is intercalated in the anode host, graphite host, gets out into the electrolyte and gives out electron which gets through the wire. Okay, and this is indicative of graphite. And the lithium which gets into the electrolyte, this combines with manganese oxide and forms this particular compound, right? So the overall cell energetic, cell potential depends upon the delta G of these two half cell reactions. So how does the cell potential vary as the battery is getting discharged? This can be broken down into the energetics of two half cell reactions. This is one half cell reaction. This is another half cell reaction. For a lithium ion battery, both these energetics can be empirically measured using a lithium based reference electrode. Okay. So, see, in a full cell, this is one electrode and this is another electrode. But you can also measure the energetics using this electrode and a lithium based reference electrode. And you can make another measurement wherein this is one electrode, the other electrode is a lithium based reference electrode. Okay, so if there are questions, we can address them in the class. But this is an important way to understand and understand how a cell potential varies and correlated to the energetics of half cells. Okay, so what is being plotted here? On the y-axis, you plot potential. On the x-axis, you plot the extent to which a battery has been discharged. So here, battery is fully charged. Here, the battery x equal to 1 corresponds to battery being fully discharged. So what is seen is that the cell potential is constant till a particular time, let's say approximately till x equal to 0.5. And following that, the cell potential dramatically decreases. So you want to be operating basically in this regime due to a variety of reasons. Okay, one, we have talked about reversibility of the cell. Okay, so that is the reversibility of the cell also depends upon the host, the structural changes in the electrode. So you don't want to be completely discharging or and so on. Okay, so we have addressed these questions in some previous lectures. So, but what we are trying to elaborate here is how do you correlate the cell potential to two other energetics, the energetics of half cell, which is indicated by the cell potential here. How do you do this measurement? You take this electrode and measure the cell potential against a lithium based reference electrode. And here we are plotting the cell potential, half cell potential. You take this electrode and take measurement against a lithium based reference electrode. So this overall cell potential is this cell potential minus this cell potential. Okay, so in a way, the ease of this happening, okay, that is this is, let's say, lithium intercalated in the anode. As the battery gets discharged, this is the reaction that is happening. So this indicates the variation of cell potential. The anode cell potential indicates the how facile this reaction is, because the reaction is less and less facile as the cell gets discharged. Okay, so so the overall cell potential decreases because the exothermicity of the overall reaction also decreases as the cell is getting discharged. Okay, so so think through this. Okay, so this is an important aspect of lithium-ion battery battery chemistry and battery thermodynamics. So overall take-home message is the overall cell potential can be understood in terms of two half-cell reactions. So in the next lecture, we will look at the battery cell potential as a function of certain kinetic factors, how function of current, how the cell potential will vary depending upon how much rate, how much current you're drawing, which is the rate or kinetic consideration. We will look at that in the next lecture. Thank you.